to review, we did the natural log function, a function that looks like this. So when you sketch it, you need to sketch it with an intercept of 1, 0. You need to sketch it with a vertical asymptote, since the graph itself will never cross x equals 0. The natural log function is only defined for positive numbers, and it looks like this. This does not approach an asymptote. This keeps going to infinity. So I'm going to put y equals ln of x, and I'm going to say as x goes to infinity, ln of x goes to infinity. But clearly that is not the same type of increase as a very rapid increase. Do you guys see what I mean if I say that that's not a rapid increase? If you want the technical term for what a not rapid increase is, it's very, very technical. We call it concave down. That's what concavity meant, that the rate of increase is decreasing. How fast it is getting bigger is getting smaller. That's the second derivative idea. So this is concave down, and this is a basic feature of the graph. We're going to do the inverse function of y equals ln of x. Y equals e to the x. This is the inverse function, the opposite. If ln of x does something, e to the x undoes that. I call this exponentiation with base e. That way, when we have other bases and you say, what is happening to x, you can call it, we are exponentiating x with a base of whatever. Just like we're taking the log of x with a base of whatever. And I remember telling you guys, either on video or before, that in higher math, whenever we say log of something, we actually do mean natural log, because that's the new default. Every time we do integrals and derivatives, it has to be in terms of e. It cannot be in terms of anything else. And we will be converting everything back to e. The graph of e to the x looks very similar to this, just reflected across that y equals x line. So I know that there is an ordered pair here at 0, 1. Isn't e to the 0 power equal to 1? What is the value of e about? 2.7 something. You guys should know it to about 2 decimal places. You should know that e is about 2.78. Even if it's just 2.7 that you have memorized, you're fine. You should know that, and coming up later in calculus, you're going to want to know like e is between 2 and 3. So it's 2.78. It's the natural base. And let's get some reasons why it's natural. First of all, the graph of this looks like this. Very, very, very skinny, and then it approaches and increases sharply and drastically. This is a very concave up graph. And if I graph that and the previous natural log graph on the same graph, and then I graph the line y equals x, and I'm going to try to graph the line y equals x as carefully as I can. Be somewhat impressed. Now, that is the graph of y equals x. Do you see that they're mirrors of each other? They're reflections. XY points became YX points. So I want to give you a couple of definitions of E here before we move on, because E is the most important number in math. It is not pi, it is not tau, it is not 1, it's not 0, it is E. The reason that this is not said lightly. It comes from multiple different fields of math, and here's one of them. If I do 1 and I add an infinitely small fraction in an infinitely large number of times, and I do the limit as n approaches infinity, so that means that that infinitely small fraction is then raised to itself or multiplied by itself the same number of times, I get the number E. So this is a thing that appears in banking a lot, where you want to do interest related to how long you have left the money in the account. For instance, let's say that I am going to have a bank account that gives me 4% interest. Now, is it fair that it does that interest calculation only on December 31st? I could theoretically mortgage my house and put all the money into this bank, and then right as that ticks over, get the benefits and then take it all back out again. Banks don't want you to do that. So what they do is they calculate your interest continually, recurringly. at an infinitely small fraction of the amount an infinitely large number of times. This calculation is the natural growth that occurs because this right here is equal to E. There's another better biological example, and it has to do with blebs. Every one of you has studied or knows that bacteria can divide. Let's just hypothetically say that a bacterium can divide once every hour. This is about a rough idea of how E. coli can split. For those going into biology, E. coli becomes one of the model organisms you use to study genetics. There's like model organisms, Drosophila melanogaster. I think the fruit fly is one of them. There's a specific mouse that's studied. Like there's all these ones that are done and well done. But basically, after 1 hour, this bleb becomes 2. Question, what happens a half an hour into that? What does it look like? I mean, if at 1 hour this single bleb is going to become 2 blebs, what's happening at a half hour? What does it look like? 2 blebs together, so it's going to be kind of like blebbing out from itself, right? Now, as it's blebbing out from itself, this second bleb gets genetic material and is actually capable of copying itself now too. So it will start dividing even though it's not finished with the first division. So it will start blebbing. And that one will actually contain just a little bit enough to start dividing itself, and it will. And then this one will, and then this one will. This is actually what it starts to look like. And after 1 hour, you don't just have 2, you have about 2.78 of these things. This is why it is called the natural log. It's a natural growth pattern that happens. So the advantages of this, of converting this to base E, or having everything in terms of E, is a couple-fold. One, the derivative of e to the x, this is the only function where this is true. The derivative of e to the x is e to the x. You're supposed to be stunned into silence now. We have encountered a function that is its own derivative, which means also that it's its own integral. The integral of e to the x is e to the x plus e. We're going to get back to this concept here in a second. But the key thing about today is going to be working with e and getting some review and practice working with e. So let's start with some basic facts of things that we kind of need to review. What's the natural log of 1? 0. I don't want you anymore to think about this as like you would have when you were freshmen and sophomores. You would have said, because e to the 0th power is equal to 1. Remember when you would have rewritten this as a log base e of 1 equals 0, and then you would have done the little loop around thing that said e to the 0 is equal to 1, and that's why. We don't want to have to do that every time. What I want you to do is actually get a visual of this graph, and the ln of 1 is 0. Okay, I want you to go a graphical approach on this. It will be faster, quicker, more efficient, and give you a better appreciation for the natural log function rather than just it's a log and I kind of have a basic idea of what a log is, but I really don't know. No, we're going to do logs in a couple of months with the Algebra 2 kids, and they love to hate them. I love them, but that's me. Okay, natural log of e then is 1. The natural log of e means the natural log of e to the first. Natural log and e undo each other. Whatever's done to one, the other one undoes. So e to the first is to exponentiate with base e. Natural log is then to undo that and brings back the 1. There is a linkage between this one and this one.
So ln of e squared would be 2.
Yep. And in fact, let's generalize and put ln of e to the k is equal to k. Okay? Oh, that was my third example. Fourth example, in the fourth one, we flip the operation, and we're going to go e to the ln of k. So I'm just doing these in opposite order. What would that be? It would be k. This is also k. You're just doing them in different orders, but it's doing the same thing. So I'm going to do a little thing here, and we're going to do some examples of some solves. Again, just a review of stuff you've done before, but an important one. What time are we out of here? I'll look that up in a second. E to the 4x, negative 4x equals 15. 33? Okay, solving these just is a review of stuff that you have to do to get the variable by itself. I'm not going to make you crazy simplify this stuff, but you do need to know basics of how to do this. First step. Before we deal with the negative 4x, what's the very first step? Divide by 200. So e to the negative 4x is equal to 15 over 200. Divide both by 5, and I get 3 over 40. The next step is to undo the next thing that's being done to the left side. And the thing that's being done to the left side is exponentiate with a base e. So to undo that, I need to do the opposite of that. What's the opposite of exponentiate? Natural log. So I'm going to take the natural log of the left side, ln of e to the negative 4x equals natural log of 3/40. And the natural log of the e to the on the left side undoes itself, and that just spits out a negative 4x. And from this moment on, you don't need to show that step. You can go directly from here to here. What's your final step? There are numerous ways to write that numerator. Remember, that could actually be the natural log of 3 minus the natural log of 40. But your calculators have the capability of using that as its input. So this is fine. You would want your answer to be in a calculator ready mode that you could plug in and just get a value. Okay, number 6. Natural log of x minus 2 squared equals 12. Option 1 here, if I look at what's happening on this, option 1 is to make this left side just be a little bit cleaner. What can I do to simplify that left side a little bit? You can bring the 2 out in front. 2 ln of x minus 2 equals 12, which means ln of x minus 2 is equal to 6. The left side is taking the natural log, a log base e. The opposite of doing a natural log is to exponentiate with a base e. And that undoes what's being done on the left side. So I get x minus 2 equals e to the 6th, or x is equal to e to the 6th plus 2. I want to show what happens when I do option 2 and see if that gives me a different result. Option 2 is to actually drop the ln right away, to say x minus 2 squared equals e to the 12th, to exponentiate both sides at the start. Why might that change your answer a little bit? What is it about x minus 2 squared that's going to make this right side just be a little bit different? Square root. What about the square root? How many square roots does a number have? What do we? So tell me those. Plus or minus is what I'm going for. Those two answers are going to be plus or minus. I'm going to plus or minus root e to the 12th, which is the same thing as plus or minus e to the 6th, and I get x is equal to plus or minus e to the 6th plus 2. Which of the two of these is more correct than the other? The right one is. The second one is because if I were to plug this into the original equation, what's going to happen by order of operations is that that negative is going to be squared and makes it a positive before you take the natural log. This is kind of throwing one of our rules into limbo, isn't it? If I do this, ln of x minus 2 squared and I say that that's equal to 2 ln of x minus 2, this is actually only true when x is greater than 2. We're not going to spend a heck of a lot of time on this distinction. I know we have really thrown this rule out at you and said, this is true, this is just something you guys need to know, but it's actually really only true for particular domain values.
So could we still do it?
You can, and you're not going to see a lot where it's suddenly going to say, solve this, and if you don't get the negative, then you're wrong. That's not the purpose. It's just building this awareness that really we can't say these properties are true all the time. We can only say they're true for specific x values. For instance, if I graph y equals ln of x squared versus y equals 2 ln of x, on the right side, x must be greater than 0. And on the left side, the absolute value of x must be greater than 0. They have different domains. This one on the left side looks like this, and the one on the right side just looks like the right half of it. So they're not always the same, and there's not a lot we can do about that right now. It's just a little building some instinctual awareness of that. Okay, next. We're going to differentiate y equals e to the x. We're going to do this using a technique that we did on the video at the start, logarithmic differentiation. And I want to prove its derivative using what we did before. So I told you its derivative is e to the x, and you're supposed to yell at me and say, wait a minute, why? Well, I'm going to build off of what we did before. What I'm going to do is I'm going to take the natural log of both sides and say ln of y is equal to the ln of e to the x, which means the ln of y is equal to, what is the ln of e to the x?
X.
That's x. Now we're going to take the derivative, and we're going to do this using chain rule on the left side. The derivative of y, remember implicit? Derivative of y is y prime, and the derivative of ln of something is 1 over. And then on the right side, the derivative of x is 1.
Why isn't it 1 over y prime?
1 over y prime. It's the chain rule, so I do the derivative of y prime, and then I do the 1 over part second. If I want to get the y prime by itself, I just multiply by a y. This tells me y prime is equal to y. See? The only function where y prime is equal to y, because y was equal to e to the x. Then we can put a little QED, which means thus it is shown, quad erat demonstratum, and I've shown that y prime is equal to e to the x. So, yay, we proved it. Now let's do like a million examples of this. I'm going to change my numbering system. I'm going to do this problem in 2 ways. One using logarithmic differentiation, the other one not. So we'll put a little I here. The first way we're going to use product rule, like we always have. I'm going to do first derivative of the second. So first is x. The derivative of the second involves doing a chain rule derivative. So what's the derivative of sine of x? And then what's the derivative of e to something? E to the something. E to the sine x. So that's product rule. First derivative of the second plus second e to the sine x. Derivative of the first. And the derivative of the first is just 1. So this is my raw derivative. Can we factor anything out of both of these? E to the sine x. Parentheses. I'm left with an x cosine x plus 1. We're going to try this again using a technique called logarithmic differentiation. And in logarithmic differentiation, you take the natural log of the left side And you take the natural log of the right side before you take a derivative. Reason being, it lets you split the right side up into two things. You don't truly have to do product rule like you did before. Ln of x plus, what's the ln of e to the sine x?
Sine x.
Sine x. Okay. Then you do the derivative of the left side, which is chain rule, y prime times 1 over y. You do the derivative of the right side. What's the derivative of ln of x? 1 over x. Plus the derivative of sine x is cosine x. Then finally, you multiply the left and the right side by y. When you multiply the right side by y, you replace what y was in the original problem. And y is x e to the sine x. And this would be fine and dandy, but I'm going to go ahead and distribute the x in so I can clear the 1 over x. I'm going to leave the e to the sine x factored out. So I have e to the sine x, 1 plus x cosine of x. So I just wanted to show you two ways to do the same problem that use different techniques but get you the same place. Most of the time, we're going to kind of be picking whether we want to use log or not. We're not going to be doing both at the same time. So let's just do some basic examples of regular differentiation. Do you want to use regular here? You can. It's probably about the same. What words am I thinking now? What's the major rule that's being applied here? Even before that, what's the rule that says that I work with the inside stuff and work my way out? Chain rule. Chain rule is huge on this. So we have to talk about chain rule, and we have to go with the inside thing first. Derivative of x squared plus 1, which is 2x. Now work your way outside. The derivative of radical x squared plus 1, 1/2 x squared plus 1 raised to the negative 1/2. And then finally, the derivative of e to something is e to that same something. Well, if you want to clean this up, there's really only one way to do it. We're going to knock the 2's out. My x is in the numerator. My e to the root x squared plus 1 is also in the numerator. And I have a denominator that has x squared plus 1 radical, so that's just radical x squared plus 1. That's it. We having fun yet? Y equals x over e to the x to the second. So we can practice different techniques. Let's do logarithmic here. So to do logarithmic differentiation, it's a good technique when you have something that just looks like it's going to be a little complex involving e's. What's the first step of logarithmic differentiation? What do we do to both sides? Natural log of the left side equals. The right side, can I split that up and make it ln of x minus ln of e to the x squared? And what is ln of e to the x squared? X squared. Do you see how in one step you've made this problem just a little bit easier? You don't have a quotient anymore. All you need to do is on the left side, when you take the derivative of ln of y, make it y prime over y. When you take the derivative of ln of x, that is 1 over x, and the derivative of x squared, 2x, and then just multiply both sides again by that y. Y was x over e to the x squared, 1 over x minus 2x. And if I simplify that by actually distributing the x back in, I'd get 1 minus 2x squared all over e to the x to the second. Two more. It's 2x squared because I moved the x in. I say two more. We're going to do one more because we're killing on time. Okay. E to the xy plus x cubed plus 3y squared equals 11. This is going to be a little bit of a review of implicit differentiation, of product rule, of all these little rules you've had. So let's go here. We need to do the derivative of xy. Do you remember how to do the derivative of xy? What rule do we have to use? Product. First, derivative of the second plus second derivative of x, which is 1, and I'm going to put that in parentheses, times the derivative of e to the xy is e to the xy. And then the rest of this we've got, plus 3x squared plus 6y, what's the thing I have to do with y? Y prime. And then the derivative of 11 is 0. Now the only thing you have to do is get the y prime by itself. And we're going to do that by distributing xy prime e to the xy plus y e to the xy plus 3x squared plus 6y y prime equals 0. Remember, we're going to get the y prime terms on one side and then non-y prime terms on the other side. Factor the y prime out and divide what's remaining over to the other side. E to the xy minus 3x squared over x e to the xy plus 6y. And just a second, I'm going to pause the video. Okay. Last problem. I'm going to take this off and just do one more on this recording that we didn't do in class. Y equals the secant squared of e to the negative 4x. And we're going to take the derivative of this. Now, before I take the derivative, I may want to write it as y is equal to the secant of e to the negative 4x quantity squared, so that when I do a chain rule, I can really keep track of this. Y prime would be equal to the derivative of negative 4x, then the derivative of e to the something, e to the negative 4x, then the derivative of the secant of something, which is secant tangent, so secant e to the negative 4x, tangent e to the negative 4x, and then the power rule on the outside would be 2 times the secant of e to the negative 4x, all to the first power. So if I keep track of all of this, I have a lot of factors, but I can't really do a whole lot with them. The only way I can actually bring them together is to bring the negative 4 and the 2 together as negative 8, e to the negative 4x. I have 2 copies of secant, so I can write that as secant squared e to the negative 4x. And I'm going to keep parentheses going, and then tangent of e to the negative 4x. So that's it.